right? In that video, we talked about kind of the fundamentals of chemistry, and I would argue this is where all of chemistry is, and virtually everything we've talked about this semester is boiling down to this single kind of concept. Okay? All of chemistry is saying I take an atom and I take another atom and I want to explain what's happening in between them. That's chemistry. Right? So when we talk about grams, how is grams talking about what's happening between those? Well, grams is quantifying atom A. How much of atom A is there? Okay? How much of atom B is there? If they go through and do this thing that's happening in between, how much do I end up with at the end? All of chemistry is really centered at that point in this entire really stupidly simple diagram. All of the math is trying to come up with ways to quantify this. Okay? Almost all of it can be done qualitatively by making some rough comparisons and some rough analogies, and we can define fairly well a lot of the interactions that we expect to see in chemistry. We can't quantify any of them because we're using qualitative observations. Okay? But this is where I think chemistry actually becomes fun and interesting, because we can use some very simple observations and make sweeping conclusions that end up being very, very accurate. Okay? So it's kind of cool. In that, well, too bad I deleted all that. So let's try that again. So in that space in between, we've got something going on. Okay? There is some force between there. Okay? And force is kind of a bad term. We're going to use attraction. Okay? And just like we saw in the video, it's like human attractions. There's varying levels of human attractions. Just because we have varying levels of human attractions, we get the same thing with chemicals. Okay? And with humans, we could look at it as couples versus singles. Okay? Couples have a very strong attraction between them. Single people have a much weaker attraction. That's why they're single. Okay? So with chemicals, we do a similar thing. We classify them as couples. There's a strong attraction versus a weak attraction. Okay? That strong versus weak, it gets classified out as bonds, which are a strong attraction, and forces, which are a weak attraction. Okay? So that's our first kind of differentiation on that attractive force, just like we have couples and singles. Okay? But just like with couples and singles, could we refine these categories further? Okay? Is a married couple the same as a couple that's been dating for a day? Okay? They have drastically different relationships. For that matter, a married couple that just got married versus a married couple that's been together 20 years. Okay? You're going to get different relationships. So we come up with different ways to classify those. Okay? With the coupling, we really just have like dating versus married, and that's all we got. Okay? Right?
It's 2019. It's a little bit more complicated. We got Tinder now.
I would argue Tinder's down in the forces area, not in the bonds area, just kind of for the record. Okay? So what we're looking at is what are those kind of classifications. Within bonds, we've already discussed bonds. How do bonds classify out? We have ionic. And we have covalent. And we learned about those when? It wasn't the very beginning of the semester.
Third week.
It was about 5th week, I believe, actually.
It was when we
We might have talked about it with Lewis structure, so we might have been in like 3rd or 4th week. So we see it a little bit with Lewis structure, and we saw it a lot in chapter 6, which based off of everybody's responses to those, what are you still having problems with, was nomenclature. How do we name compounds? What's the first differentiator we use for naming compounds? Ionic versus covalent. Right? That's how we differentiated them. We named them. We have different rules for naming them. Why? Because we can evaluate that they have different strength bonds. That allows us to differentiate them, which is kind of cool. Okay? As we continue through chemistry, we find that that needs further refinement. Because if I gave you, say, the compound HC versus HCl, those have very different properties. Okay? HC, okay? If I threw a compound at you with HC in it, you'd probably just be like, that's why are you throwing just chemicals on me? That's just weird. I feel it evaporate. That's pretty boring. But if I throw HCl on you, you're probably not like, why is this evaporating? You're probably like, why am I melting? Okay? Those are drastically different properties. And yet, if we look back at our definitions for covalent versus ionic, both of these compounds are covalent. So we need something to differentiate our covalent compounds because some of our covalent compounds have drastically different properties. Right? So what do we introduce as our term to differentiate them? We introduce the concept of polar. Wow, let's try that again. Polar covalent versus non-polar covalent. Okay? That simple addition of a word allows us to classify the bonds a little bit differently, and that helps us to do something about predicting their ultimate reactivity. Okay? In this case, it's not changing anything to do with nomenclature. Okay? We're just differentiating them. Why? Because maybe we can come to conclusions further on down the line. Okay? So we have 3 primary categories for our bonds: non-polar covalent, polar covalent, and ionic. So what we should be able to do is to look at a bond. What is a bond? It's between 2 atoms. That's good. What's between 2 atoms?
Attraction between electrons.
It's ultimately a pair of electrons being shared between 2 atoms. And that's what's causing that attraction. So I should be able to look at a bond and say that is non-polar covalent, ionic, or polar covalent. Okay? So if I look at the compound or the bond NaCl, you should be able to tell me very quickly that that is. It's interesting. We've got a couple different words there. How do we know which one that is?
It's ionic because it's a metal and a non-metal.
So just because we have the terms doesn't mean we know how to use those terms. Okay? Ultimately, those definitions come from looking at their strength. Okay? The nonpolar covalent is an insanely strong attraction. That insanely strong attraction coming between them has to do with the properties of those materials or those atoms. That property being electronegativity. Okay? So the larger the difference in electronegativity, the weaker the attraction between them. Okay? The less that difference, the stronger that attraction. Okay? The problem with using electronegativity as a definition for each of those? Anybody know what is the problem with using electronegativity to define each of those bond types?
What's the standard?
What do you mean, what's the standard?
Well, what's insanely strong for a bond could be considered 2 very different things by just about anyone. So you can't just set one specific number. You have to be at the, like an electronegativity of two for you to be polar covalent? Or
You would have to define those exact numbers. So for it to be ionic, it needs to be a difference in electronegativity greater than some number. Okay, so I have to establish that standard. But by establishing that standard, what do I also need to know? To have a difference of electronegativity between 1 or 1.7, which two atoms are going to give me a difference in electronegativity at 1.7? Okay, I like the face you made. Yeah?
I mean, like numbers memorize.
What numbers?
Electronegativity.
How many of you have memorized electronegativities? That's not a very useful definition then. Okay? If we don't have the electronegativities memorized and it's not on the periodic table, we can't use that as a definition base. Okay? We can establish a standard. Even with that standard, we don't have the numbers to use. Okay? So what do we come up with instead? What's our easier version that we might call a rule of thumb? And in this case, for an ionic compound, a metal and a nonmetal. Just for the record, non begins with N. In case you were curious. Okay. So sodium chloride, sodium is a metal, chloride's a nonmetal because
The staircase indicates whether it's a...
we're using the staircase off the periodic table because we always have the periodic table because we're awesome people like that, also known as chemists. We know that. Okay? So what if I give you what's that one?
It's the weird one. It's like, it's ammonium something.
Oh, is that 4?
Uh, Really?
I was looking for H1 on the periodic table.
Is it a C?
For 81? Oh my gosh. Is it really that bad? Fair enough. Let's just try this here. Make sure we're all on the same page.
What else? Okay. Fuck it up.
Is that better?
That's much better.
Okay. So I'm hearing a couple people shout it out. Ammonium chloride. Cool. I didn't ask for the name. What bond? Tons of different answers just got shouted out. That's fun. I heard some people say ionic. That's because chlorine's a metal. Okay, is nitrogen a metal? Is hydrogen a metal? Okay, so then it can't possibly be ionic. And yet, that's ionic. I didn't say you were wrong. Okay, which of course is going to be the follow-up. I said it was ionic. Okay, why? Why is it ionic? That doesn't fit metal versus non-metal.
The difference in electronegativity.
The ionic definition that we're using is a rule of thumb. Ultimately, our difference has to come back to differences in electronegativity. Okay? So we have to be careful when we go through and branch out to these other compounds and recognize that there will be exceptions to these because these are rules of thumb, not perfect definitions. Okay? Is there a giant hint in this compound that would allow us to know that it is ionic? I kind of know what you're going with, Kyle, but I'm not quite. That might help if I spelled ammonium right.
Ammonium's from positive. I remember that being a weird thing. I don't think there's any.
Ammonium is the, say it again,
The only positive polyatomic.
the only positive polyatomic ion. What's the connection going to be between those two compounds? Ionic because it's an ion. It's in the name. Okay? We don't have to just say metal and nonmetal. We have to acknowledge, are they ions? Metals and nonmetals will very typically be ions because large differences in electronegativity between metals and nonmetals. Okay? There's plenty of other cases that we have ions, okay, without it being a metal. Okay? Yes?
Could you look at it with the difference between hydrogen and chloride, the electronegativity, figured out that way?
It's a little bit more complex there, which is why I've been trying to dodge that question. Okay? So we're going to still dodge that question. There is another observation that we could make. So you've addressed what NH4 was. What was the other one? Chloride. What is chloride? What is the symbol for chloride?
Cl.
No, it is not Cl. Say that again?
Cl.
It is Cl negative 1. How do we know when we say chloride, we're referencing Cl negative and not chlorine?
It's a chlorine ion. Sorry.
Because
The D.
that D in our name tells us that we're referencing the ion. Which ion? A negative one. That's why we've changed the suffix to be "ide." What is the name of a negative species? And what? Ion. What's the connection? It's an ionic interaction. Okay? That was there to help for a little bit of review on the pieces of nomenclature as well. Okay? Polar covalent, non-polar covalent. How do we differentiate? Are any of those ionic bonds? No. Which one's non-polar covalent? Which one's polar covalent?
CC is nonpolar.
Why is CC non-polar?
Because they're both the same.
Why is the same to same relevant? Again, the difference in our bonds is coming back to electronegativity. The ionic one had a large difference in electronegativity. If I try and get as far away from the ionic as possible, what am I going to do? Have the smallest difference in electronegativity possible. What is the smallest difference you can have? 0. Same atom to same atom. Our non-polar covalent is as far away from being an ionic bond as we possibly can be while still being a bond. So rule number 1 for identifying our non-polar covalents, same to same, because I don't have a whole lot of space. Okay? That definition is phenomenal. It's too narrow though. So we expand it just a little bit. We expand it to include carbon to hydrogen. Okay? How do we know we have a polar covalent compound then?
Anything else?
If they're opposites.
Everything is.
We come up with the extreme definitions for the ionic and the non-polar covalent. If it doesn't match one of those, we're left with polar covalent. Okay? It is the easiest way to differentiate these, again, as a rule of thumb. It's not an absolute truth. The absolute truth requires
Memorization of every.
electronegativities, okay, which could be a memorization. It could also just mean pull out a table of electronegativities and just look at the differences. Okay? Typically, when we're trying to deal with qualifying properties of a compound, we're looking at the rules of thumb and we're not looking at absolute, because the rules of thumb get us darn close enough. Okay? So because of that, we stick with those. Okay? So that allows me to look at any compound, any formula, and identify the bond types. Well, what do I do with the bond types? Okay? That just tells me something about what's happening within the molecule. Okay? So that could be cool and useful and interesting, but do you only care about yourself in the world? No. You also care about your interactions outside the world. So now that we know what's happening within you, what can we do? Expand and bring in another person and have them now interact. That's now shifting us into our forces. Okay? What are the forces that we have? Okay. So can I clear everything?
Yes.
Cool. What are our forces? Ionic, not covalent, because covalent is a bond. Dipole, dipole. London, you mean all I had to do was read off the slide? Yes. Well, it's there. Those are our forces. How many bonds did we have? We had 3 bonds. And we have 3 forces. Look at that. If I take a look at a compound that has one particular type of bond and I now pair it up with something else that has the same type of bond, it's going to generate a force. I can now qualify the name of that force. So these forces all have origins coming back to the bond nature. If I take a look at an ionic compound, sodium chloride, and I now want to see its interaction to sodium chloride, how do I name that new interaction in between? Right, well, I could break down and look at what the individual pieces are. One piece was positive and negative. Why is it positive and negative? These are not partial charges.
We balance out the charge of electrons.
These are formal charges because sodium is +1, chloride is -1. A +1 species would be a cat what? Ion. What's the interaction? It's an ionic bond. What's the interaction in the blue one? It's also an ionic bond. So what would the attraction be between 2 ionic structures? Ionic. You mean it's all the same thing? That's how creative we are in naming our forces. Virtually all of the forces that come out of it tie back to the bonds that make them. Because that can be confusing, someone went through and said, we should not call it just ionic because we want to differentiate the bond from the force, which is why we get the term electrostatic. Make sense? So the ionic or electrostatic forces are coming from ionic bonds. How do we know we have an ionic bond? 2 ionic molecules. How do you know they're ionic?
Their charges.
Metal and a nonmetal. What would I expect? Never mind. Ignore that. But I'll redraw it. Let's move to the next one down. Yep. Yeah, let's be creative. Why not? Everybody likes creative people, don't you? Appropriate response. What is the attraction now? What is our purple interaction? They're nonmetal nonmetals, so what do we know it's not? It's not ionic. Okay, cool. You're like, oh, that's dumb. Dude, that's how you should do this. Rule stuff out. That's awesome.
Non-polar covalent?
Okay. Now we run into, well, how should I name this? Okay, so I like the idea of referencing bonds, so let's go back and look at the bonds. What are the bonds in the first HO? That would be polar covalent. What would be the bonds in the CO? Polar covalent. So that would be polar covalent, polar covalent. Didn't work. Okay. What does it mean to be polar covalent? What does it mean to be polar? You have opposite charges. Do we have opposite charges forming in each of those individual bonds?
No, because they're both the same.
Do hydrogen and oxygen have the same electronegativities? No, they're different. They, by definition, don't fit our nonpolar covalent. They're in the everything else, which means the oxygen is starting to steal those electrons from the hydrogen, which means what happens to the oxygen? it becomes partially
Negative.
negative. It's accepted more electrons. What happened to the hydrogen?
Partially positive.
What happens to the carbon?
Partially positive.
It is partially positive. And the oxygen is
Negative.
partially negative. Why did you know the carbon was partially positive?
Because the oxygen is also partially negative, and
I-
it has to attract to the negative oxygen,
Why do you know that oxygen is partially negative?
because it's on the periodic table is negative 2.
Oh, no.
It's a higher electronegativity on the periodic
It's
table.
electronegativity.
Yeah.
How do you know the electronegativity? Does anybody see the electronegativity on there?
Trend.
Electronegativity trends.
The electronegativity trends. You mean the trends that I told you to memorize way back when, back in Unit 1? Yeah, those exact trends. Yeah, those ones. Because ta-da! There it is. We get to use it. That's why we need those trends. Right? So we align the positive to the negative here. Why?
Opposite attraction.
We want stability. We're trying to cancel that charge, so we can align those. Okay? Back to the name. We still want to come up with a name for this. Okay? It said polar. When we said polar, you said an interesting phrase. What were you referencing when I asked about polar covalent?
Two opposite charges on the end of on the other side.
Two opposite charges. Okay? On opposite ends, kind of like a magnet. So we got the north end and the south end, also known as the north pole and the pole. So we could call it two-pole. We could call it bipolar, but that was already used in relationships, so we can't do that. We would use di as our Greek prefix. So that first molecule has a dipole. What does the second molecule have? A dipole. What is the attraction in between two dipoles? Dipole. Really? Yes. Welcome to the creativity of chemistry. What was our force for an ionic bond? Ionic. What was our force for a polar covalent bond? A fancier rearrangement of saying polar covalent. Okay? It's dipole.
It's fun to say.
Okay? Which, dipole or the polar covalent? Yeah. Okay. I like dipole better. I might reference it as dipole for the rest of the semester. Dipole. It's the dipole. That's pretty phenomenal. Okay, so that's cool. That covered polar covalent and ionic. Did we cover them all? No. So what do we end up with?
The intervals.
Okay, so let's do hydrogen to carbon and let's do carbon to carbon. What is the attraction going to be between those?
Polar covalent and
H to C is
Hydrogen.
non-polar covalent. That fits our hydrogen to carbon definition for a non-polar covalent.
oh yeah, that's right. And
Carbon to carbon is same to same, so
Bipolar covalent.
non-polar covalent. Are there any charges? To generate a charge, what did we need? We needed a difference in electronegativity. By definition, what is the difference in electronegativity for non-polar covalent? 0. Are there any charges? No. Is there any reason for those molecules to interact? None whatsoever. So what might we do as an approximation for this? Would I expect there to be any attraction? No. If there's nothing there, do I really want to name it? I probably don't want to name it at all. Why name it? It's like naming nothing. Naming nothing was actually kind of an important discovery, but different conversation, math class. All right? So we might go through and say that interaction isn't worth naming until some jackhole comes along and says, yeah, actually it is. Okay? That is an important interaction. There is something happening there. It ain't big, but it's something. That something is enough that we have to take it into consideration. Because they've now gone against the standard logic, what happens? They get to name it. And what names do we end up with? You get a crap ton of them, actually. Van der Waals was the name of the guy that kind of hypothesized this, I believe. I need to go back and actually reference that. London dispersion. I made up something in the video. I swear to God, I have no idea what it is or why I said it in the video. I completely made it up. I think there's zero truth to what I said in the video. Right? Something about he was on London Bridge. I don't know. Did completely BS. Right? The other name that can come out of this would be induced dipole. Meaning if I take this structure that has a bunch of electrons and I bring it near a structure with other electrons, what are the electrons going to do? They're going to move away from each other. That small shift is now inducing a dipole because the electrons now repel one from the other. As the electrons repel away, what gets exposed? The nucleus. So I have a partial positive charge forming and a partial negative charge. That's an induced dipole because the action of the molecules getting near each other has allowed an induction in motion.
So,
okay? Like if I won't do this, but like if I creepily started standing closer and closer to someone, what's going to eventually happen? You're going to start to move away. Okay? That would be an induced dipole. Just the proximity is causing someone to move away. Same thing's happening with our chemical molecules. So we're a couple hands, 1, 2.
So those two molecules repel each other?
It's not so much that they repel each other, it's that their electron clouds repel each other. Because the electron clouds repel each other, it exposes nuclei. Those nuclei are now attracted to those opposite charges.
So do they actually bond, though, when that happens? Or?
So and this is where we have to be careful. Do they actually bond? What are we talking about here? We're talking about a force. And when we talked about our spectrum of interactions, this force is at the extreme bottom. Where's our bond? Do they actually forming a bond? No. Are they forming some attraction that we need to take into consideration for how those two molecules might interact with their outside environment? Yes. What would those things be? Pivnert. Pivnert is where this is coming from. Our ideal gas law comes back to London dispersion forces. Your question.
Instead of like saying that you're measuring the degree of the relationship between these two, it's more like compatibility, right? Where they may not have a reaction or a relationship.
I would argue it's more a proximity. The closer that those atoms get to each other, the more of an effect they will have on each other. That effect is not a large effect. Okay? And so when we look at a compound that has nonpolar covalent bonds, we can now say that that compound's interactions with the outside world are now going to be incredibly weak. Those incredibly weak forces that we might have neglected to begin with, we can't neglect, and so we have to name them. The name of that force is these guys. Our London dispersion, van der Waals, induced dipole, induced dipole. All of that is a mouthful. You'll only see me write LDF. Okay, for London dispersion forces. Okay. The point of this is what we can do is now identify a bond through Lewis structure, chapter 1. Okay? And we can now take that bond from two different molecules and bring them near each other and say, well, what the hell are you going to do? Okay? That what are you going to do is those forces. I can now use those forces to draw conclusions about what I would expect those two things to do. That's pretty cool. Okay? Kind of, sort of? Okay. So, 3 bonds, 3 forces, right? I know it was a little while ago, but I didn't think it was that long ago. There aren't just 3 forces, there's 4 forces. Well, really, actually, if we look, somebody seems to have structured this slide to draw attention away from hydrogen bonding, because hydrogen bonding is not fully externalized, for lack of a better word, flush with the rest of them. It's indented, which would suggest it's not such a cut and dry force. And in fact, hydrogen bonding isn't a cut and dry force. It is a special circumstance. Okay? What do you guys know about hydrogen bonding? Do you know of any particular compounds that might be hydrogen bonding? Okay. H2O. OH. And if I look at H2O, I might see something like that. That interaction, what might we classify if we ignore hydrogen bonding? What are the bonds found in this OH? Polar covalent. What are the bonds found in the other one? What kind of force occurs between two polar covalent bonds? A dipole-dipole. So we might classify that interaction as a dipole-dipole. And we would be correct. It is classified as a dipole-dipole. How often does that interaction happen? Why a lot?
Water everywhere.
Water makes up 80% of the Earth, and in fact, if we think back to chemistry, we've used water consistently throughout the entire semester, both in lecture and lab, because it is the most common solvent. Okay? Why is it such a good solvent? Lots of things contribute to it. One of those things is that attraction in there is incredibly strong. Why is that attraction so strong? And to give you a hint, Garza touched on it earlier. Garza. One of your classmates. It's okay. Electronegativity.
They're opposite in electronegativity.
If we look at our electronegativity trends, oxygen and hydrogen are on the complete opposite ends of the spectrum for electronegativity. If we look at that polar covalent bond, that bond gets as large a difference in electronegativity as humanly possible without formally becoming ionic, which means that is a massive partial positive and a massive partial negative, which means the attractive force there is insanely strong. Okay? It's not quite ionic, but it's a hell of a lot stronger than a dipole-dipole.
So when you mean insanely strong, what do you mean by that in terms of what we comprehend as strong? Like, is it...
That question is way more complicated than you will even ever approach knowing. Who's the strongest person in this classroom? Is it really me? I don't think so. Or we can pick me because I'm the one in front. So yeah, I'm the strongest person. So if like Game of Thrones, right? The mountain came into the room and stood next to me, would you really say I was all that strong?
Fight him and find out.
No thanks. Okay. Strength is a big relative aspect. So when we're talking about stronger, that interaction is a very strong dipole-dipole. It is not as strong as ionic bonding because we haven't formally formed charges. Okay? But it is such a strong interaction, and it is such a common interaction that what might I want to do? Give it its own name. What name do I decide to give it? Bob would be a phenomenal name, believe it or not, and a hell of a lot better than the name we've given it. Because the name we've given it seems to suggest that it's a bond. It's not a bond. Okay? That is a force that happens when we have a dipole-dipole interaction, and we also have present hydrogen chemically linked. I should really say chemically bonded, but I have a hard time saying that word in this case. Chemically bonded to oxygen, fluorine, nitrogen. Because water just wants to have some fun. Like the song. Water just wants to have fun. I don't know the lyrics to that at all. Okay. That has to be satisfied for us to have hydrogen bonding. Those are the basic pieces in review of that video that establishes them. Once we know what those are, what can we do? We can take those interactions, look at a compound, classify its bond type, classify what forces it has, Once we know the forces, we know something about the strength of the attraction, and we can use that strength of attraction to predict its melting point or boiling point. Okay? Predict how it dissolves in other substances. Predict even how it reacts with other things. For the sake of this class, what do you have to deal with? Phase transitions and solubility. You actually want to learn something cool? Reactivity. Talk to me in a year when you take OChem1. Because that's reactivity. And it all boils down to being able to manipulate this. It is a massively important subject that gets way too little play in Gen Chem. Okay?